Hi, welcome to Mara and I's final presentation for the Open Inquiry Experiment. As you may remember from our midway presentation, our goal was to answer our research questions regarding the trends of water quality within the dorms of AUC, because we had often heard of people who had issues with their water quality in some rooms and other people not having any issues. So we did a preliminary study to find that there actually was a variation in perceived quality at least. And after meeting with the caretaker, we found that there was only one source of water for all of the dorms. So we formed a hypothesis that the rooms farther away from the source would have more pipes to travel through, and thus the water would accumulate more dissolved solids, which we would be able to measure. So we got to around 50 samples around the building and analyzed their water quality for total dissolved solids. Unfortunately for our hypothesis, we ended up not being able to identify a statistically significant trend regarding the water quality in the dorms. However, we identified a few issues that we intended to improve on in the next iteration of our experiment, most notably an issue with the oxidation on the wires. As our measurement tool sent a current of electricity through a tube of water via exposed wires, it caused a chemical reaction for an oxidized layer to form on the surface of those wires. This ended up continuing to build up and impacting our data as we continued to measure the samples. We tried a few methods to recalibrate this data and remove the effect of the oxidation, but we still could not find a correlation between the water quality of the rooms and their distance from the source pipe. As we couldn't find any evidence for our hypothesis at the dorms, we decided to try to improve our measurement capabilities and apply them to a new hypothesis on the surface bodies of water in Science Park. The quality of canal water in Amsterdam is always put to question, and while walking in Science Park, there seems to be some bodies of water that are much more polluted than others. After a quick survey to find around 30 individual bodies of water, one of our first hypotheses to test was whether the proximity to roads would have an effect on the water quality. However, the processes of nature that dictate water quality are very complex and usually don't rely on one linear relationship. So as we recognized that there were likely many factors that could have an impact on the surface water quality, we tested two additional predictive factors, which were the proximity to green space and the proximity to business areas, to do a multiple linear regression. From this, our new research question was to determine what were the most predictive factors for the water quality among the roads, the business areas, and the green space. For this experiment, Mara gathered our samples in the field with our own homemade technique to collect water samples in 30 bags for each water body. And once we got our samples, we tested them with an improved version of our previous methodology. As a quick review, our sensor measures total dissolved solids from its relation to the conductivity of the water. We can do this because pure H2O is non-conductive, and only the dissolved solids, such as the salts and their ions, conduct the electricity. These dissolved solids are used as a metric for drinking water quality, with good water quality ranging from 50 to 250 ppm. So, we send an electric current with an Arduino through a tube of water in which we know its volume, and then our Arduino program computes how many dissolved solids exist in the sample based on how well the water conducts the electricity sent through the tube. The main improvement that we made to our methodology from the last one was removing the issue of the oxidizing wires. So we cut new wires every 3 samples, and you can see that there was no longer a trend in the order of the samples taken. Then, we improved our precision uncertainty by altering the reference of the Arduino from 5 volts to 1.1 volts and changing the resistor of our breadboard. Essentially, we changed our code and our research setup to capture the expected area of TDS, the 50 to 250 ppm, over the most amount of bits in the analog reader so that we could improve our precision of the TDS measurements. The graph depicts the TDS calculated in the code per bit that we received in the analog reader, which you see is from 0 to 1023. So the most amount of bits that we can fit in our expected area has the highest precision. With our measurement methodology improved, we analyzed the data utilizing the Geographic Information System program QGIS. This allowed us to create maps and analyze our data spatially compared to other aspects of the environment. We wanted to assign 3 proximity values for each of our predicting variables of the roads, the buildings, and the greenery. So first, we created heat maps with a scale of 1 to 10 proximity for each of these variables. Then, the average proximity value for each area of the body of water was calculated for each of those variables, and then they were used as an independent value to predict the dependent value of the water quality. We did this all in Python with a multiple linear regression to see what factor can explain most of the variation in the water quality. Here is a visualization of the data that we collected during our second experiment. As you can see, there are about 30 water bodies, and we have the levels of TDS from 0 to our max, which was 163 ppm. After collecting the data on the water quality and the level of proximity for each water body, a scatter plot of the multiple linear regression can be seen by this graph. Each line of best fits for the independent variables represents how much its proximity positively correlates with the water quality. And along with this graph, we have coefficients from the multiple linear regression. These values, such as the road coefficient that you can see, represent that with each increase in the proximity level, which was from 0 to 10, the TDS increased 9.32 ppm. As each proximity level was standardized to be 25 meters, we can see that the road coefficient was the highest, as every 25 meters that a water body was to the road, the TDS should increase 9.32 ppm. This value also had the lowest p-value at 0.0023. And we can also see that the proximity to buildings had a slight effect with a coefficient of 3.14, and the proximity of the green had almost zero effect on the increase of water quality or decrease. This leads us to our final map, showing the most impactful variable, the proximity to the main road, and how we can kind of visually see its impact on the water quality of each water body. Our uncertainties for this iteration of the experiment are almost the same as the midway presentation, with a few changes based on our improvements. For the cross-sectional area and the length of the tube, which we used in the calculation of the TDS, we still have the same uncertainty in regards to the step size of the ruler. For the resistor, we just changed the resistance, but ended up having the same process of determining the uncertainty with the step size of 1 ohm and the 3% measurement uncertainty. And for our analog bits, which is the final variable in the equation to determine the TDS, we have the same uncertainty as well, as we're collecting the same amount of bits. To determine the total propagated uncertainty for our calculation of TDS, so that we can know the uncertainty of the measurement value that we're using in our analysis and its uncertainty budget, we again adopted Forrest's code from the Jupyter Notebooks lecture notes. And here you can see that our biggest uncertainty was from the resistor and the bit reading. This ended up giving us a slightly lower uncertainty than our last experiment, with an expected value of TDS at 76.7 plus or minus 1.3 ppm. So after all of these calculations, what are we able to say about our research questions and hypotheses? First of all, we assert that we are able to represent the TDS of the water samples with our measurements. The TDS data varied from 80 to 160 ppm, with a total uncertainty of plus or minus 1.3 ppm. The variation is much bigger than the uncertainty of calculating that variation. Now, are we able to correlate this variation with any of our predictor variables? The predictor variables of the proximity to the buildings and the roads both had a p-value below the standard alpha of 0.05, which were 0.04 for the buildings and 0.0023 for the roads. From our multiple linear regression coefficients, our research goal to find which of the variables that were able to explain most of the correlation was accomplished, as we could clearly see that the proximity to the main road was the leading factor. From this experiment, we've learned a lot about modeling real life and the difficulties of predicting and understanding natural trends. Our initial research goals were fairly broad, with the intention of studying trends of water quality around Science Park by testing different hypotheses. We came out with a solid understanding of the requirements for a successful experimental setup and found a viable trend in surface water quality around the area. But to broaden the impacts of our results and work towards further research, we've come to realize the importance of a scientific background for understanding the relationships in the natural sciences, as the more that our models reflect real life, the better they will succeed. Thanks for watching.